Ready. Okay. So, howdy everybody.
Hi, Dmitry.
Thanks for coming. It's the last session, so it's kind of hard on people. My name is Dmitry Sagatelyan. I'm a software engineer by training. Do you hear me okay? Good. I have a master's degree in computer science, and I switched to using LabVIEW 20 years ago, and not going back to text programming anytime soon. I'm also a certified LabVIEW architect and a LabVIEW champion, and I'm a regular presenter at NIWeek, CLA summits, and Bay Area LabVIEW user group. My main areas of interest include actor programming and using contemporary software engineering methods in LabVIEW design, which includes Agile principles and solid principles. So I usually know what I'm talking about because these are my two favorite topics. Back in 2009, I started a LabVIEW consulting company, Architect Technologies, in San Francisco Bay Area, and I am now a full-time LabVIEW consultant. So if you need an independent design review or are starting a new project and need help with your architecture or need a second opinion, I'm your guy. Having said that, the topic for today is a brief recap of solid principles, because I'm not sure everybody are using them every day. Usually it takes an hour. I'll try to squeeze it in 15 minutes, so that would be quick. Then we'll talk about what is actor programming best practices, how using solid principles affects your actor designs, and finally, messaging topologies. This is the last presentation, and there is a good chance that I would go overboard. Maybe 10 minutes, maybe 30, maybe an hour. So 5 minutes before the bell, we'll decide what to do. And the folks who like to hear the finish of the story, they may stay, but I'll try to stay in time. Okay, no questions so far. So, in the February, I'm sorry, I'm tethered. I'd like to move a lot, but I cannot today. In the February of year 2001, 17 developers gathered in a ski resort in Utah, and they all were known as stout opponents of the heavyweight, document-driven software design processes. And despite being anarchists, in 3 days they came out to an agreement and penned two very important documents. The first is the Manifesto for Agile Software Development. That's all it is. And the second are the principles behind the manifesto. And I found one of these principles so important to me that it is now on the back of my business card. And it reads, simplicity, the art of maximizing the amount of work not done is essential. And I'll try to show you a couple of examples of what I mean by simplicity today. In 2003, one of the guys, Robert Cecil Martin, also known as Uncle Bob, published a book, the classic one I always show in my presentations, Agile Software Development. And probably for the first time, he gathered most of the best practices in Agile development in a single book and put them in order. And that gave birth to the solid principles. As you can guess, this book doesn't have a single LabVIEW diagram. So it may be hard on you guys because all examples are in C++. But I find this book so important. It's probably the most important book on software engineering and architecture that I read in the last 15 years. So even if you don't have a taste going through the C++ examples, get the book and skip the examples. It's worth reading. And I'm serious. I'm telling this, the audience, for 4 years. some people heed the advice, and they're really, really glad they did. Okay, last year, Uncle Bob published the second long-awaited book, Clean Architectures. It covers the same topics as the Agile software development, but from an architectural view. There are no examples in C++, maybe one. And it touches on the subjects that evolved during the 14 years between the two books. And if somebody was on at the Lava barbecue yesterday, we had a raffle and 2 people got this book. So I hope they will read it now. Who actually read either of those books? Not many.
20% of one.
1, 2, 3, 4, 5, probably 10 people. Well, that's not good enough.
I bought it, finally.
You bought it? Okay, so that counts if you promise to read it.
Yes.
So the guys who bought or read it, read it, after the presentation can claim the solid ribbons if they don't have one already. Okay. So 3 quotes from the first book. We live in a world of changing requirements, and requirements change in ways that the initial design did not anticipate. It's hard to kind of not agree with that. So our goal is to make sure that our software can survive those changes. And the value of solid principles is that if you follow them in your designs, you have a much better chance in adapting your code to changes in requirements at incremental cost. And the way to do is refactoring. And refactoring becomes feasible the cost because you only touch the classes that were directly affected by changes in requirements. That's the value of solid principles. What also comes with it is the reuse level of your code. As is, if you have a PPL, it can be plugged into a new application and reused, is substantially improved because you have less coupling between the classes. And finally, using solid principles enables design of plugin architectures without any extra effort, thanks to the dependency inversion principle. So in the book, the Agile design principles, there are 2 groups. One are the solid, the topic of today, and we have 5 of those. Single responsibility, open close, list of substitution, interface segregation, and dependency inversion, which makes the solid abbreviation. And they are applied at the module level. In LabVIEW, these are classes and libraries. This is what we do as software developers every day. And there is a second group of principles that are applied at component level, which are packages in LabVIEW or PPLs. And they tell you how to package related classes together so they can be distributed natural way. And there is some mapping of those principles on both levels, but I'm not going to touch this today. Read about this in the book if you need to distribute stuff. Design smells. Also from the book, they are very similar to code smells, but it's called the design smell if it happens at the application-wide scale. So these are really bad things if you have them. And some of them, you probably heard rigidity, fragility, viscosity. I'll mention that one. Doing things right is harder than doing things wrong. And needless complexity. So that's the number of the page in the book. And on a side note, I have a lot of presenter notes that refer to specific pages in the book that would make it read easier for LabVIEW guys, because I did this presentation with LabVIEW developers in mind. I would use one example theme throughout the presentation, which is a biological sample scanner. And this is a scanning microscope. It is the heart of a next generation DNA sequencer I worked on when I had a full-time job. So I know this pretty well, and it serves as a good example of hierarchical system. So what it has an XY stage. Sample is there, it positions the stage. It has a Z stage to focus the camera. It has the camera, a light source over here, excitation shutter to shut off excitation without switching off the source, and a filter wheel to get the right wavelength. And this had to be designed in a way so it can be seamlessly integrated into a bigger system, for example, by putting fluidics on board to improve your system throughput. And you need to have a GUI to monitor stuff and start the run. And you need to have some safety feature which uses interlocks. So that's the example. Let's briefly go through the principle. First, single responsibility principle. It says a class should have only one reason to change. Sounds simple. And this is an example of a blatant violation of this principle. This is a monolithic scanner that combines the workflow implementation with driving all the devices. You cannot reuse any of those outside of this class. Never do it. Yeah? It's really easy to do this. Break out the individual device drivers into separate classes and just call them from the scanner. That's essentially what it does. It's a trivial example, and I think most people already do this. I didn't see a monolithic thing for a long time, but maybe I'm just lucky. A more subtle violation of these principles, if you can see, there are load configuration and save configuration methods in a class, which gives the class a second reason to change. If your configuration format is changed from INI to JSON or XML, you need to touch this class. If instead of files you want to use a database, you need to touch this class. One class is okay, but if you have 50 classes in your application, you have to touch all of those. And this wouldn't happen at incremental cost, because after touching the code, you need to test it, then you need VNV resources, and it takes time to do that. So an easy way to do that, that works in 90% of cases, is to load the configuration elsewhere and just inject it, pass it to the scanner as a cluster, then the scanner works, and when you destroy it, it passes out the latest configuration. This is the simplest way to do it. It doesn't work all the way, because if you need to, it's called dependency injection, by the way. If you need to save or reload configuration while the actor is working, it doesn't work. So there are ways around it. I'll talk about those later. The next principle, the first most important, is dependency injection. It says that high-level modules should not depend on low-level modules. Both should depend on abstractions. Not really clear, but substitute modules by classes and abstractions by interfaces. And it says high-level classes should not depend on low-level classes. Both should depend on interfaces and dependency in UML sense. So what you do instead of the previous picture, you create abstract classes that do nothing and serve like interfaces. And then for each of the devices, you implement this interface. And your workflow implementation for the scanner is statically decoupled from the concrete device drivers. So you can substitute a device driver for a different camera, the Sony camera, and you're fine. Your scanning workflow code doesn't change. So that's pretty obvious. And one thing that comes with it is an inversion. It's called inversion of ownership. People noted that if you create interfaces, they're more tightly coupled to their caller than to the classes that implement it. So what this inversion of ownership suggests is you package dependency interfaces with the class that uses them, with the class that needs them to perform its functions. And this is really essential for plugin architectures, because packaging for plugins is an important thing. There is a second part of this principle, which is a lot more cryptic. Abstractions should not depend on details. Details should depend on abstractions. Does it sound useful or practical? No, it doesn't. Because we don't know what Uncle Bob did meant by abstraction. And he has one of the best definitions of abstraction I saw, page 194. Abstraction is the amplification of essential and the elimination of irrelevant, which also doesn't make practical sense. So let me show you how to very simply apply this principle and get a lot of value out of it. So you have a sample scanner and you want to implement this class so it can be reused without changes on a different make or model of this microscope. So essentially what it needs to do is to abstract the workflow from unnecessary details. And the first question you ask, what is essential for the sample scanning workflow and what is not? And if you ask that question about the light source, filter wheel, and excitation, you would see that the only thing that sample scanner needs for the workflow is to set the color and intensity of the excitation. It doesn't need to know what kind of light source this is, whether it has a shutter or a filter wheel. This is non-essential. Same thing with the camera. It needs to snap an image with a certain integration time, and it shouldn't be concerned with having images in focus. This should be guaranteed that when it does snap, images are in focus. So instead of directly calling the camera, you create an imager interface with this single method, implement it. For this microscope, it would involve a CCD camera and a Z-stage, and the imager implements the autofocusing, and when it gets a snap, you know that the image will be in focus. So you abstracted your workflow from details of how you take images. The third subsystem is the sample. Sample scanner doesn't care about the X and Y coordinates of the images it takes. It needs to know what row and column of the titer plate it is. So the sample API would move the XY stage to a certain image position, to a certain sample position, not to an XY coordinate. So by asking what is essential and what is not, we essentially defined a set of APIs that make sample scanner reusable on other makes and models. So that's its value. And it's very easy to ask yourself what is essential and what is not. And once you start doing it, it's, like breathing fresh air. I live in San Francisco Bay Area, and when I come to some big city and get out of the plane, sometimes it's hard to breathe. But in San Francisco, you just don't notice how good the air is from the ocean. And the same would be with applying this principle. You wouldn't understand how you did it before you started practicing. Okay, so let's get to the part A. If your sample scanner cannot be statically coupled to concrete device drivers, then who would create objects of those device drivers? If sample scanner creates it, then it would be statically coupled to them. We cannot do that. So enters dependency injection design pattern. It's not a principle, it's a design pattern. And what it essentially is in software engineering speak, it is a container. What you do is you make a conscious decision to separate your application code into reusable classes that you want to reuse on other applications, and application-specific code. And typically this container, which is a class, is called an assembler class. And what it does, it creates all the objects from reusable classes because it knows everything about the types of the devices. It's application-specific. It configures them, loading the configurations from database or a file, JSON, XML, whatever, and it injects the created objects into the subsystems. So this is the bring up process. And then finally, it just runs the main VI or whatever you have, main actor, and you're done. And when your application stops, it properly does the bring up of the application, releases all the resources, makes sure that all devices are in safe state. This pattern is used with solid principles, and it makes the biggest impact on how your code is structured. This is a very important thing. This is a UML diagram for dependency injection. So you have an assembler class which is application specific. It creates the imager because it knows what it does. It creates the sample scanner, and it creates and passes the imager to sample scanner. These guys are decoupled through a well-defined interface, so they statically don't depend on each other and can be used separately, reused separately. That's pretty much it, except one thing that is really important to LabVIEW developers. Assembler object has the lifetime of the entire application. It doesn't go out of memory until the application finishes because it is the application. Yes, sir.
Mind your muzzle on the laser, okay?
Oh, I'm sorry. I'm sorry. But you're not a pilot. I'm allowed to do it.
My wife says no.
Okay. This is a presentation grade. This is a presentation grade laser.
Yeah.
It won't hurt you.
Yeah.
You know, I had a black spot in my eye.
Yeah.
I once was hit in an airplane. We had an airborne lab
Yeah.
with a 4 megawatt laser, and I got a reflection from that infrared beam. So
Ouch.
I know how this is for, first hand. This is not for the record. Okay, so the important thing is that the lifetime of all the references created by the assembler object is the application lifetime. So if your actors or objects go out of memory, the references stay valid. This is really important for plugins. And it is just achieved by design, no extra code plumbing. So this is kind of simplicity in action. Open-close principle. Software entities should be open for extension, but closed for modification. Here's what it means. You have a Pike camera. I'm not shining it. Alan. And it implements a blocking snap method, which exits only when the image is exposed, integrated, and read out. So this takes a lot of time on the caller loop. And you need to extend it by implementing an asynchronous snapping, so your caller loop can do stuff while for several seconds the image may be processed. And the normal way to do it, well, not normal, the typical way to do it is you start editing your class, and you may break it, or your class may be used in a bunch of other applications, and they will be broken or need to be revalidated. So never do this. This is the wrong path. The right path is create an asynchronous Pike class, which is a child of the base Pike, and add the asynchronous feature there, and override the snap method there. Maybe with a different name, so you can do it snapping synchronously and asynchronously. And this would not affect any of the applications that use the old Pike camera driver. So you don't have to revalidate. This is incremental cost. You can refactor stuff easier this way. List of substitution principle is a pretty obvious one. Because what we do, the scanner doesn't know anything about the concrete actors or devices it works with, but it needs to do something, right? There is a contract on each method that says what the input should be, what the method does, and what it creates as an output. This is a contract, like, for example, which errors it returns. Maybe it generates some events. That's a contract. So the principle says subtypes, child classes, must be substitutable for their base types. So they need to fulfill the interface contract. Otherwise, the scanner would not be able to properly behave. In this case, you have an interface method set home, which takes x and y in inches. This is why your scanner uses the inches to call them, or your sample subsystem. Now your system guys bought a German-made stage, which takes input in millimeters. You should not call them directly. You should wrap this stuff in another object. Yeah, do a facade pattern or something to keep your functionality intact. This is an obvious thing. A less obvious violation is, again, your system guys bought a cheap XY stage that doesn't support soft home in hardware. So what you do when you implement it, you return an error. But this error is not in the contract. Your scanner wouldn't know what to do when your driver throws this error. Right? So never do this. You may want to just ignore this thing because there's no functionality, but then your sample scanner will position to the wrong position, right? Doesn't behave normally. And the right way to do it, if something is defined in the contract of an interface method, you should simulate it if it's not supported by the hardware. So this principle actually enables using the dependency inversion and open close. Without it, you're uncertain of what your runtime object would be doing. Okay, I already said that. Yeah, there is a programming language Eiffel. Bertrand Meyer, a French guy, defined it like in the late 90s, which natively supports design by contract. The compiler knows on preconditions and post-conditions of each method and can use its checking capability to actually do some checks at compile time instead of runtime. So this is good. But LabVIEW doesn't support it. So what we can do to verify that our concrete classes do not violate the list of substitution principle. You can write unit tests that define the input conditions and the output ranges and whatever, and for the base class, for the interface, and you can run them on a concrete class to verify what's going on. That's what you can do in LabVIEW, and you should do it if you're kind of using this principle. The last one, the fifth, is interface segregation principle. Clients should not be forced to depend on methods that they do not use. Sometimes this is called fat interfaces. So an example is we added fluidics to our scanner, and fluidics need configuration, and sample scanner needs configuration, so you create a configuration handler class object, and they call it directly. And this is the interface that kind of satisfies needs of both classes and the assembler. This is called the fat interface because sample scanner doesn't need all this stuff. And the drawback from this approach in LabVIEW is that when you take sample scanner and drag it to a new object, it would drag the configuration handler interface with it, which would drag the fluidics class with it, because this interface is statically coupled to fluidics configuration. So these guys are not, sample scanner is not reusable. And the way to get around it is create the interfaces for loading and saving configurations of which So now you have two interfaces specific to your two subsystems, and your configuration handler should implement both, right? No, this is not possible in LabVIEW because you have two inheritance arrows, and LabVIEW does not support multiple inheritance. So this is possible in C++, but not LabVIEw. And you need to do stuff to get around it. There is a sample code and a document I put, I think, on the LabVIEW best practices that tells you how to support multiple interfaces in LabVIEW without real interfaces in G or multiple inheritance. So if you're interested, you might go there. Okay, I told that. So I'm done with the solid principles. These are the two books. And this is the tool you had before you digest these books. And I got my hands first on the first one, 2011. I'm still rereading some of the chapters when I need them. So it's a wise investment. And what comes with it, when you digest the books, the content, instead of hammer, you have a nail gun. And you would never bend a nail again. So that's the value. Some references, this is the general stuff, the two books and a classic paper on the dependency injection pattern. If you don't know Martin Fowler, go to his website and read it. And by the way, the slides are available for download. These are the presentations that were given over time at NIWeek on the solid principles. So this is just one of them. And these are the use cases that I did using solid principles. So lots of stuff for LabVIEW developers to digest. Let's switch to actors. If you look into Wikipedia, it lists 3 models of process interactions. The first one is implicit model. That's an example. G-compiler does this for us. It breaks diagrams into clumps and runs clumps in pseudo-parallel fashion, depending on how many cores you have, etc. If you have PGA code, they are mapped into Fabric, and they run through the parallel in real time. I won't be talking about this. We're blessed with this implicit model. Not many languages have it, just a few besides LabVIEW. The second one is shared memory model. You have 2 threads, and they need to communicate, producer, consumer. So you take a local variable, a global variable, whatever, action engine, and push data from one loop to another. And I'll talk about it to underline the problems you get when you use shared memory. And the third one is message passing. It's also available in LabVIEW, and this is using queues, notifiers, events, whatever. So shared memory model. You have a common value table, and your XY stage updates it at regular intervals with current X and Y. And your UI reads from common value table and displays the values. Everything is fine. No issues. Oops. Then you add a Z stage, which is independent, used for focusing. And it also writes a Z to common value table. And you get a race condition. Because after you get this, your value of CVT is cached, and it may become stale in the Z stage. So your updates may get out of sync. Very hard to detect. Sometimes they may be critical. But smart people back in the 60s and 70s designed locks like semaphores. Yeah? And semaphores take care of race conditions if you manage to lock the critical code, critical access code, and it is a time. So that's good. That's not the whole story, because when you start using locks,
Yep.
You get an even worse dragon, deadlocks. It doesn't scale nicely. Or it doesn't scale nicely, and you know the manifestations are much worse. Here you only have like your results would be somewhat different in most cases. Here your application just stalls, and you need to kill it and restart it, right? And the easiest way to create a deadlock, for example, we have thread A and thread B, and they use a camera and shutter, and they need to log those devices, and they log them in different order. This is the simplest way to achieve a deadlock. And both of these things are notoriously hard to reproduce and debug. And I couldn't, resist putting Edgar Dijkstra quote here: if debugging is the process of removing bugs, then programming must be the process of putting them in. So that's what we do when we use the shared memory model. Extremely hard to debug. And that's what C++ developers have to deal with every day, unless they use actor frameworks. Okay. So, actor model of computation. Back in 1973, Professor Carl Hewitt of MIT formulated the actor model of computation. He worked in the field of artificial intelligence, and he was interested in behavior of parallel systems. And that model includes actors, which are universal primitives of concurrent computation. Messages are universal units of communication. Actors exchange messages. Messages are not shared. Once a message leaves one actor, it stops having access to that message. And there is some security used with enabled by stereotyping. And when an actor receives a message, it can send a message to addresses of other actors. So that's a message transport. Address is a message transport. Create new actors and designate how to handle the next message by changing its own state. That's the three things can do. And there wasn't much interest until in this actor model until late 90s, when multi-core computers started arriving, and when you start getting virtual machines, clouds, clouds and computer farms. And then there's suddenly, 15 years ago, everybody wants to do this, and at this moment we have 55 actor frameworks implemented in 22 languages, including LabVIEW. And where this plays really big in the text programming language world, for example, Java and Scala, is the cloud computing. They use it extensively to create reactive systems. Okay. So what's an actor in LabVIEW? Very simple. It's a message handling loop. This is your state, lives on a shift register. This is your mailbox. You get a message and you do something with it. And the messages are not shared, and the actors don't share their internal resources between them. So no race conditions, no deadlocks, right? Unless you introduce them inside the actor loop. So we still need to be careful. And things that can introduce deadlocks, for example, are blocking request reply messages. So you still need to watch for that. Types of messaging architectures. And I didn't mention, but this presentation is framework. I'm not talking about specific frameworks here. It's just general stuff. I'll have a couple examples or snippets of actor framework, couple examples of my stuff. I use a message broker. So it's framework agnostic. It's relevant to everybody in that sense. So data-only messages, this is what I use. I have a strictly typed message class, which inherits from the abstract message. And in my case, it has a subject. Every message has a subject, a double value, and this is a message with double message with units, string with units. And I use a send method, which is part of the message transport. This is a message transport interface to send it to destination. And this is what happens on the receiving end. You have a user event, for example. You check if it's a double with units. If it is, you take the value of the subject out and the value out. And if the subject is revolutions per minute, then you update the proper indicator. That's pretty much it, what the data messages are. In case of executable messages, which is the second big group, the message can contain both can contain executable payload and optional data. And we know this as actor framework. Actor framework is based on command pattern. So we have a lot more moving parts here. There is an actor class. This is like a counter actor. I took this example from Stefan Lemons from the actor framework community group. So you have a library that has a class inside with 4 methods, public methods. Methods may be simple, just a plain by value class. Each public method has a message that would be sent to it. And the message in itself is a class, and each message has 2 methods. Send itself to a destination and execute its payload. Usually it's created using a tool called Message Maker, so you don't have to write this boilerplate code, which is kind of nice, because otherwise you would be just writing this code by hand. And the way it happens, this message sends, this send call sends the message, it sends itself to the actor core. Actor core takes it and executes it unconditionally in this spot. And then, unconditionally executing it, it calls the do method on the class, and you get your increment. So a lot of more moving parts, just because you're sending executable payloads. And if you need to set arguments with it, if your method needs like add instead of increment, a value to add, you put it in this class. And there is a bunch of frameworks in LabVIEW in both groups. And the better known one here, the only one known here, is the NIWeek framework. It happened around year 2010. Who uses actor framework? Probably a quarter of the room, maybe a third of the room. In the data-only messaging, we have the LabVIEW around circa 2010. We have JKI state machine objects. Who uses JKI state machine objects? 1, 2, 3. 3.5. Who uses DQMH? 1, 2, 3, 4. A little bit more. Then there is a messenger library by James Powell. Anybody uses it? All these things are available on Tools Network. I see one hand. And then I have my proprietary one. It's called Message Broker, and that's the snippets I'm showing you here. I finished in 2015, and I already presented it at the CLA Summit in Austin in 2015. And the presentation is available, so you can download it from GitHub. Okay, so that's the big picture what we have in the LabVIEW domain. Now let's switch to the actor programming best practices. On the CLA Summit in 2004, Dave Snyder, better known as Duckloop, gave a really, really good and important presentation on fundamentals of actor programming. He gave a half-an-hour presentation on the same subject at NIWeek 2013. If you're interested in this, you just must read it. He talked for an hour about things I would be covering in 15 minutes. Yes, sir.
His presentation was so good, and he was very gracious to allow us to pull that presentation into the Actor Framework class. That's how good that presentation is.
Oh, you mean community? Oh, class,
No, course. The course.
the course, yeah.
Actor-oriented design in LabVIEW. A good chunk of the slides in the first 45 minutes are Dave's,
Yeah,
which he permitted us to use because he's that kind of nice guy.
okay. Is Dave here? No.
So by all means, go read that. I'm
Yeah,
backing
read
up on
that,
this.
and I talked to him like yesterday about it, and he said, well, maybe I need to put an effort and update it and present it next NIWeek. So I think we should encourage him. So these 4 methods are from the presentation. I concocted this one, and the other 2 are from Actor Framework. So briefly go through them. Actors do things to themselves. Actors can receive any message at any time. What these rules mean is when you design an actor, you need to keep this in mind. That's what they mean. Actors are not job processors. My staff callers have no jurisdiction over message priorities. Avoid using self-message sequences. Avoid using blocking request-response messages. Personally, I find it too limiting, and I have a valid and safe use case to use them. And avoid using direct messaging, message along the actor tree. I also find it too limiting, and I do otherwise. Yes, sir.
I will point out at this juncture that the best practices for Actor Framework say to avoid, not don't do.
Don't do.
Yeah, we don't say don't do it. We say, there are places where reply messages are not optional, where you just have to use them. That's the thing you have to do. And there are situations where allowing peer connections between actors instead of up and down the tree are also permissible. But we want you to really think about what you're doing.
Yeah.
In those
So
instances.
that's what avoid means to me.
Yeah. That's just to clarify. Avoid
Yeah.
doesn't mean, dear God, don't do this. It means, consider if you have a better choice.
Yeah, they are not absolutely evil like the go-to statement,
Right.
but they may be unsafe.
I liken the reply messages to bullets. If you need one, you really need one, and if you don't need one, you should not use them.
Okay, thank you, Alan. No, I didn't shine on this one.
I continue to appreciate that.
Okay, so let's briefly go through these 6 things. So, things are not done to an actor. Actor does things to itself. That's the basic principle. Messages are, for that reason, messages are requests and not commands. If you send a message to an actor, it may choose to drop it. It shouldn't execute it unconditionally. Maybe sometimes this is okay, but you need to have a choice based on the actor's state, whether to do it or not, and in which order. Actors do not share its state and their internal resources with other actors. They only communicate through messages. That's the core of the actor model. Otherwise, you start getting shared memory problems. An example is a sample scanner actor may try to lock a camera actor to use it exclusively, but this is against the best practice. The right thing, if this camera actor starts working on behalf of the scanner, it should block itself from receiving any requests from others and either log and drop them or return an error or whatever you decide as a developer. Another example, you see the actor core VI here. Since actors do things to themselves, they don't have to unconditionally execute the do methods.
10 minutes.
Okay, I am way over time. Is this entertaining?
Yeah.
Okay, so I should keep going at the same pace. If somebody needs to go out, just go out. But you wouldn't get a solid ribbon.
Oh, there you go.
I got you, right? Okay. Actors can receive any message at any time. So why this happens? Because the caller, the parent actor, already has the actor's address. And you can never trust your parents. They can send your address to other actors. right? So you need to be prepared to handle messages from sources you don't anticipate by design. Actors send messages on their own schedule, which means they are not aware of your state. If you receive a message, you need to think whether to process it now, delay it, or drop it. So that's a design consideration. Actors have to gracefully handle unexpected messages. That's the bottom line. This is a snippet from my stuff. So here I receive a message, and I look at what is the subject. And if the subject is the command shutter state, I know it must be a Boolean thing. And then I cast it to Boolean, take the value, and either close or show or open the shutter. What happens if it is not a shutter state? Then I say, well, I log a message and set an error that it is an unsupported message, whatever that would mean for the detector. And this is normal. You may get any message at any time, even unexpected messages. Just ignore them in this case. But report them so developers can figure out something is going wrong. Maybe it's a bug. Maybe not. And in case the type is wrong, it's definitely a bug. So I set an error and log it that message name type is a mismatch, and I need to fix it. That's what that best practice means. Actors are not job processors. So well-behaved actors should process incoming messages as they arrive without creating message backlogs in their mailbox. This is one of the cornerstones of David's presentation. Yes. So what to do if you have a lengthy one? You create a helper loop, and it should execute the longer action on behalf of the main actor loop. It should not be blocking to the actor. The third one, actors may decide to keep some subsystems as by-value objects. Not every subsystem has to be a class, right? That may be unnecessary complexity. And in this relation, during the lifetime of your actor, by-value objects may be refactored into helper loops, and they may be refactored into nest detectors, and vice versa, depending on how your requirements change. So there is no hard boundary that a helper loop stay forever a helper loop. It depends on how your actors evolve. Having said that, for the actor model, actor model of computation, this doesn't matter. It treats both actors and their helper loops as actors. But from the practical viewpoint, for us as developers, there is definitely a difference. First of all, helper loops are designed to handle a single task. They should be simple. Second, helper loops should not be visible outside of their actor, ever. It's an internal resource, don't share it. The message transport for helper loops may differ from the main actor transport message. It might not be like priority queues, like an actor framework. Might be a notifier if you need the lost stuff. Another big one is actors. The true actors extend the actor class. It's their child. Helper loops may be just implemented as a method in the class. This is an example of having two actor loops, helper loops, producer and consumer, implemented in a method inside the actor class. You just launch them, and then you go into your actor code or whatever that is. Blah, 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 blah. The problem with spawning actor loops is that you're splitting your data bus, your state of the actor, into several segments, and they tend to get out of sync. So when you do actor loops, make sure that you keep your actor state in sync all the time. Otherwise, it can get really confusing. So that's extra work that you pay, extra effort you pay for having actor loops. Avoid using priority messages. I asked a couple times here if somebody uses priority messages. The answer was yes. But what I think is that if you introduce helper loops, then priorities become unnecessary. Because actor has time to process all the messages as they arrive, so you're okay. The second one, even more important thing, is that actors themselves are responsible for their state and their behavior. And by setting, and caller, by setting a priority on a message, tries to interfere in the responsibilities of the actor. So don't allow callers to set priorities on the message. This is a design smell. And if you absolutely need priority, then review how you assign the responsibilities between actors. Maybe you did it in the wrong way. So the last one, if you still need priorities, the maximum number is 2. You need to have regular messages which are added to the queue end, and you need to have interrupt messages, simple messages, which are injected in front. 99.9% of messages should be regular messages, and only things that are cancel something should be interrupted. And again, your caller should not set a priority. It should be somehow hardwired into the cancel message implementation. The one thing that is important also is if you have number of helper loops, they need to be interruptible. If your actor receives a cancel command or stop command or whatever it's called, it needs to stop all its helper loops until it can stop itself. And if the helper loop is not interruptible, if it takes 5 seconds to finish something or an hour to finish something, your application will stop. So when you create after loops, make sure you put in some plumbing to interrupt it in the middle of something. Okay. Avoid using self-message sequences. This is less important, but from the readability viewpoint, it is important because it is harder to understand business logic which is implemented with self-messages. You need to go through whatever messages, message classes if you're using command pattern, or the case frames inside the actor to figure out how this all plays out. It's much easier to look at the data flow diagram and see what's going on than to look at the sequence diagram. These two do the same thing. It's much harder to understand the sequence diagram, at least for me. But occasionally I use sequence, self-message sequences because they are interruptible. Yes, sir.
Do you consider a helper loop communicating with its actor message handler as a self-message?
No. No,
So
no.
it's okay for the helper loop to send an actual message?
Of course, it's not a self-message.
Okay.
Self-message is sending something to the tail of your mailbox or to the head of your mailbox, your own,
So
not
the
the
message
helper
handler
loop.
itself sending the message to itself versus the helper loop
Yes,
sending the message
yes,
to the
yes.
message.
That's normal communication.
Okay.
I mean, even if you, I've run into this where I've got an API about launching different things or something. So I'm using the API functions on itself in order to, that way I have a consistent pathway. Maybe another module wants to do the same thing. Is it still not a good idea, or
Do your API methods result in sending a message to itself?
Yeah.
Yeah, it's a bad idea.
Okay.
And if you're doing it in a blocking mode, then you're in a deadlock.
Right.
Yeah. Yes, Alan.
So a case for those self-message sequences is, if you're allowing for the possibility that, I would like to process anything that's in my stack of messages before I do this next thing. But that does raise the specter of my state may have changed. I may be trying to make a state change happen, and I don't want those messages in my queue to be executed because they'll be handled differently.
Yeah.
So yeah, it can make for some really weird,
Really
it can
hard
get some
to
really
do
weird
stuff.
errors that way.
Yeah. So the rule is that, but again, as I said, sometimes you have to do it to cut corners. Don't consider it a permanent solution, but the plus is they're interruptible. If you get a cancel, it would cancel on before the next step. So use your own judgment on this. Okay, avoid using blocking request response messages because they'll get you easily in deadlocks. That's number one. The most often case of using blocking request response is to get a value from another actor. And this is just bad coding practice. So if you have lots of get values, you need to reconsider how you interact between actors. But the safe and really important use case for using blocking messages, blocking request response for me, is implementing complex workflows. When you program actors and with non-blocking messages, you have to design your sequence diagrams. They're hard to read, they're hard to follow, it's hard to debug stuff. If inside your helper loop you have a diagram like this, and these are the blocking messages, it is safe. And it is easy, and you can use your execution highlighting and put probes on the wire. So this is probably the most important use case for blocking messages that I see. Yeah.
Also, you may be working with an external environment or interface where you're compelled to do it.
Because they're blocking by nature.
If your actors are backing a web service, you're going to have at least a couple of places where you're going to have to do command response.
Yep.
Because we don't get to change HTTP.
Yep.
So.
Yeah. I don't have time for this, but I'll probably submit a 7x7 presentation on this topic to the CLA Summit in September. So you will be able to upload it if you're interested. Download it if you're interested. Okay. Now we're getting into solid, not solid. We're getting into command pattern and solid principles. Actor framework came out in 2010, I believe. I looked at it and I got inspired and I said I never used command pattern before. They did a lot of actor programming with the normal message handling loops. This was back in 7.1, no classes. So I said, okay, I want to test the waters. And I did a 10-week project. I tried to implement the features I use daily in my programming in Actor Framework, keeping backward compatible. So I wanted to use Actor Framework as the baseline and just extended functionality. But the changes were too drastical, and it deviated into its own framework. And the main things were, I wanted to split the functional aspect of the actor with its messaging aspect. In Actor Framework, they are the same. Actor class is a child of actor. I wanted them two separate hierarchies. So this is the component, actor component, that's messaging, and actor correlates in here. And it has an object of an actor class. That's the state of the actor. The second thing, I wanted to ensure zero coupling between actors by design, for which I introduced actor API classes. And so this is a base class, and they list all the send messages, all the send methods for all the messages that the actor supports, and messages are wrapped inside this class. And if you have a single API, it's easier to control. You can create a child of it and reuse it, etc., etc., etc. Then I wanted to fully decouple actor components, the actor core, from message transports. Actor framework, you do the priority queues, and that's pretty much it. I wanted to completely decouple them and introduce an abstract message transport layer. And I wanted to have publish subscribe from the very beginning. And I did it in 10 weeks, and it worked. And I never, yeah, that's same as actor framework. And I never used it on a real life application. And that was my feasibility with the command pattern. And I didn't fully understand the reason why. I know it now, I'll be shared in the next slide. But it became so heavy, I couldn't justify charging my customers by doing the overhead. And one of the things is that with command pattern, you have to design your own tools. And I didn't have any, people in the community that are willing to undertake that. So I got stuck with command pattern, and I don't use it anymore. And I became smarter after that. And some of the artifacts, I reuse them in my other frameworks, like completely decoupling the message transfer, etc., etc. So that's the lesson. Now let's look at how actors and solid principles do together. If you use data-only messages, you have a strictly typed message, and one actor creates and sends it to another actor, and that actor receives and processes that message. These two guys are statically decoupled from each other. They're coupled to the abstract message type, like the double with units you saw. And this is good. You don't introduce any coupling by using the data-only messages. So, solid compliant, because solid is about decoupling stuff from each other, statically and at right time. Now, in case of the command pattern, this is an actor framework example. What you have is you have a caller class, which requests something from the nested actors, so it calls a concrete method. This is the high coupling solution, and it's not recommended to use it anymore. And this message, request message, calls directly the nested actor class. So caller is statically coupled to the nested actor, and if it needs a response, nested actor is statically coupled to caller. Many people mentioned this yesterday in the actor framework stuff. So why is it bad? If this is a if this is a shutter, it can only work with one implementation of the scanner, sample scanner workflow. So what actor framework does, it says only use zero coupling solution. And what that is, for each public message, this is the response. For each public message, you create an abstract class, and it is implemented by a response class, etc., etc. And somebody has to inject it inside the nested actor, probably at startup. And this was kind of extensively discussed yesterday at Casey Lammer's presentation. But this is what you have to do to decouple nested shutter from central scanner. And what dependency inversion principle says is that callers, high-level modules and low-level modules should not depend on each other. They should depend on their abstract interfaces. So to be solid compliant, you need to do it the other way, and then inject the concrete message into the caller, which is kind of a lot of plumbing. This is the roadside tension. Yes, sir.
You generally get a lot of mileage out of zero couple up to caller and low couple down to nested, where
Yep.
the nested actor is a base class, virtual base class. So it just defines a set of messages, and then you inherit from that.
Yeah, and you covered it in your presentation here.
Yeah.
And this is a link to Alan's presentation on the same topic in Madrid. So you will be able to read it.
And,
What?
and I'm doing some stuff with malleables that might make this even better, but
Yep.
Stay tuned.
Yeah. So this is the second place where I bring up simplicity, the art of maximizing the amount of work not done. So This is simple by design if you make decision to stick if you make a decision to stick with data-only messages, you don't have to do extra work to be solid compliant. And why you need to be solid compliant? To adjust your code to changes in requirements and incremental cost, to keep your code highly reusable, and to enable plugin networks. So if this is important to you, that's the potential side.
That's the friction. That's yeah, I can't argue.
But on the other hand, I talked with John Lakanis. He has another flavor, his own flavor of command pattern that is close to actor framework. And we agreed that it's not that simple. Data-only actors have their overhead, and there is a risk of huge case statements which get out of control. So depending on your specific requirements, your types of applications, you need to consider where you win and where you lose. For me personally, for the types of applications I do, command pattern is beyond my reach, because I value solid compliance for the above reasons, and I don't actually have any savings from those huge case statements.
Your command pattern solution on the previous slide is almost identical to my solution, and it is very heavy. And just like the actor framework, when you couple class, you have class explosion.
Yeah.
When you have your ID slows down.
Everybody can hear this?
You pay for it.
You pay for it dearly.
But one point I just wanted to say, you said that AF executes every message, whereas data-only messages can drop messages. But in reality, AF executes the do, but do can decide to drop the message based on its state variables. So technically, AF can do.
But it is not enforced by actor, right?
It's per actor.
Well,
you can
yeah,
decide,
yeah.
so technically it is.
Technically, you can do this. This complicates the actor design because you have to call this function in every message. Whereas in the data-only stuff, you can call it before the case statement, for example.
Well, maybe
Well, there are trade-offs,
will
yeah.
drop messages that it doesn't support automatically without calling the do.
Yeah.
And so does the Y as well.
Yeah, so here's another viewpoint. So
Yeah.
you need to decide how you want to do it.
There's a state pattern implementation for actor framework that's very straightforward that will let you change how you respond to a message very simply.
Okay.
It does add a few classes, but they're usually pretty thin.
And do you teach that?
I do.
Okay.
It's
I never went to your class, so I didn't.
Yeah, I gotta get you a copy of that of the materials because I think it's
So
yeah.
the bottom line, if you're interested in doing due diligence, look at that training course. Okay, so let's sum up with actors and command pattern. If you count the number of files you need to decouple caller and nested actor from each other, with all the tricks, you have 5 extra files per public message in the actor class. And for me, this is a lot. It stresses your LabVIEW IDE, which is not ready for the message class explosion. And just loading 6 files instead of 1 stresses the load time. Yes?
If you set,
Can you be louder?
if you put your queue or self-queue inside the message you send, as a special way of having a response message.
You mean like a self-addressed message?
Yeah, he said that it sends a data message back.
Yeah.
Then you don't have to make all this injection. You can just say, I sent this and I will receive a data message containing data type.
You don't need to make these injections, but this still stands, right? You have to have this statically decoupled to each other. So less 1 file in that case, 4 files per public method.
Yeah.
Yeah. So that's another way to do it.
There are
And again,
ways.
we had a really nice, really lively discussion yesterday with Casey Lama's presentation. How do we inject this? And there are different options and different opinions. Okay, so I should run this faster. So for me, this smells the commands pattern, not the actor framework, the command pattern in general, whatever framework we use. For me, it has a smell of viscosity. It's harder to do things the right way than the wrong way. In this case, zero coupling or solid coupling is harder than just than the high coupling and opacity. So the main message of the presentation is actor designs based on command pattern are solid and friendly. And the reason again is, like at rip current, you have to make effort to go against the current to keep your code solid compliant, which I don't have to do in the data-only messages. Again, whatever fits you better, but you need to make your due diligence before you choose a framework. And to do that, take a low, small scale, low priority, real life project, implement it in your framework of choice. Then the second step, when it works, do some changes in the requirements and try to implement them and see how much time it takes. That's your maintenance effort estimate. And then do a code review with your team and solicit their feedback. And you need to make an informed decision. Don't jump into any framework, especially the command or pattern-based framework, unless you do this. I talk to many people who, like field architects from NI, encouraged to use actor framework because that's the only thing available to general public essentially. And they regretted it because they were not ready and they didn't do your diligence. This doesn't say that actor framework is bad. It says that they didn't do their due diligence. So don't fall in that trap. And actually, I really like actor framework for many reasons, but I don't use it for a bunch of other reasons.
It is that complaint is why there is a 3-day actor framework course, is to make sure that you will
Yeah,
truly
but
understand
it's still a rip current. You have to work against it, as against the command pattern.
We're working on it.
Yeah. And there is no way to cure it except for dropping the command pattern, which is not possible.
Talk to me next week.
Okay, we can continue this conversation.
We'll fix everything.
Yep.
Okay, so I'm done with solid messaging topology. This is a quick one. So there are essentially 3 messaging topologies. One is the direct messaging. And this is your sample scanner, and you have a shutter, and you have a camera. And a camera object wants to know the state of the shutter before it takes an image. So shutter would send its state to the camera. You can do it on small scale. You don't want to do it on large scale, because eventually it would be very hard to understand what your system does and to troubleshoot it, because you start getting fuzzy boundaries on your subsystem. Your imager is influenced by the global context. Global context is always hard to troubleshoot and to test. Second one, this thing actually increases the configuration and runtime coupling of independent actors, because they need to open a connection, they need to know about each other. This is not good. And probably these are the reasons that actor framework discourages doing it unless you really understand what you're doing and you really would benefit from doing direct messaging. The second method is hierarchical messaging. What you do, the shutter goes all the way from the scanner into the camera, and everything is hunky-dory, except that you add propagation delays to the messages, which may or not may be important, because Alan says that they are minimal. But what is important to me as an architect is that those messages cross the abstraction layer boundary, and that the scanner actor doesn't really suspect there is a shutter. It still has to forward the message to the camera. So you need to decide how to do this. And so if you include message forwarding code into an actor that knows nothing about another actor, for me this is a smell of single responsibility principle violation. It needs to do with function, and it also needs to forward messages. That's a smell you need to think. It's not necessarily bad, but you need to decide, is it important for you to get rid of the smell or not? And again, in my opinion, and probably Alan's, as he said, this is too restrictive, and you need to be able to get around it in cases that are justified. So there is a third method, a hybrid method. And you can look at it as a message bus. I just came up with this. There is no paper that mentions a hybrid method in this context. So what it does, you create a message bus which is implemented by publish subscribe probably, and your shutter publishes to a topic which is called shutter state, and your camera subscribes to a topic which is called shutter state. And this can save the day, and yeah, I use this stuff all the time, so that's the messaging topology I'm using. To properly use this hybrid messaging, you need to understand the difference. Not all messages are equal. The first type of messages are requests and request response. And their characteristic is they send to a specific address or actor, and they require their request that actor to carry an action on behalf of the sender. This is request for a future action. This is where you can deadlock if you're doing a blocking call. And the second one is event. This is a message issued by an actor that notifies others, it doesn't know who, because it doesn't keep the list, of a change in the actor state that already happened. It's a change in the past. And the hybrid messaging method encourages using direct messaging for events and hierarchical messaging for requests. That's the key thing. This is the safe way to do hierarchical messaging. Again, this is maybe efficiently implemented using publish subscribe. And this publish subscribe creates a data bus for the entire application. And I'll show you an example. And one warning, the terms message, event, and request are highly overloaded, and the way I use them here may not match like the reactive programming domain or some other programming niche in the literature. So this is only in the context of this presentation. Don't get confused. So the example, but let's talk about system aspects. What I observe is that most real-life systems have multiple aspects. The first one is functional. They perform a certain function. It's their purpose. They were designed for that. Then there is a safety aspect. And for example, in this case, you have interlocks. You open doors, and all stages must immediately stop, not to hurt you, and the excitation shutter should close so you don't get a laser beam in your eye, like I do, right? And then there is a system monitoring aspect, because you need to know a 3-day run of a DNA sequencer, where is it, right? So you need to monitor what's going on in here, and probably you can go on and on and on. But single responsibility principle says a class should have only one reason to change. So the problem is, how do you fulfill all these requirements of aspects that are not interrelated in a single class? This looks like you'll introduce a lot of coupling, because camera, because the shutter, maybe it doesn't need to know about internet. Maybe it doesn't, I don't know. But this is a big question. And the second question, yeah, so this is how it goes. You had the shutter topic, so camera knew about the shutter. Now the safety aspect adds an interlock topic to the interlock. which publishes its state. And the GUI is interested and it subscribes to it, and the shutter subscribes, and the Z stage subscribes. So you got the data bus. But the question is, these three aspects, they are independent of each other. You don't want to couple stuff. And probably the guy who designed interlocks put out a message that the shutter does not understand. They're independently designed. You don't want to couple them. So how do you solve it? And the answer is you need to do cross-aspect message translation without coupling the source code of these different aspects. Otherwise, you get your application really fragile. You change the format of interlock messages, and it stops working properly. Shutter doesn't shut anymore. Nothing can do. And the way to do it is really easy. I don't have it in my message broker yet, but I know a way to do it. And this way is to generalize the model behind each of the actors. Here's an example. A simple shutter has a single state variable, whether it's open or closed, and it takes one command, shutter open, false, or true. This wouldn't help you to interpret and react on the interlock message. What you want to do is improve your shutter implementation without actually semantically coupling it to the interlocks. You don't know about the interlocks. So what you do, you add a second state variable which says enabled, and the second command which says enable disabled. And if the shutter, when shutter gets an enable false command, means disabled, it checks whether the shutter is open or closed. If it's open, it would close it and then disable itself. And in this case, yeah, so that's a better design. Then there is an issue that the messages might be incompatible. Interlocks may publish strings that designate the state, and shutter may be just a Boolean message. And there is a simple way to kind of convert one message to another. You get the message from the interlocks, check whether its interlocks are open, closed, translate the message, guess what it says, create a new Boolean message, shutter false, and you got the proper message. This is how you decouple different aspects. But if this code would be executed either in the interlocks or in the shutter code, you get them coupled to each other. And you cannot afford that, right? This is against the solid principle. They would be statically coupled. And there is a nice way to do it if you're doing solid stuff and use dependency injection. That's what I said. They should not be coupled. And the thing is, when you create the publish and subscribe, they are created in the assembler. This is the application-dependent class, the only application-dependent code that really knows the model of the shutter and the model of the interlocks, and it knows that the shutter should close on interlocks. Instead of just pushing, just transferring the message transport of the shutter to the interlocks publisher, it also passes it the abstract message translation class. And this is a concrete implementation of this guy. So this subscription is done in application-dependent code. Things are decoupled through abstract translation message, and you're statically decoupled. And it is really easy to do that. Oh, great. So essentially, I covered messaging topologies. I don't think I want to hold you now unless you're really interested. What I have left is how to do a publish subscribe, and whether it's good or not. It sucks, really. So instead of doing even a nice, solid, compliant publish subscribe, and subscriber and publisher are decoupled through interfaces, you don't want to do that. A lot of problems, including actor initialization order, because publisher needs to provide an interface for subscribers to subscribe. So a publisher needs to run first. And in a complex system, this is a severe restriction on the order of actor startup. This makes your life really, really hard. So don't do it. There is a way around it, and there is a well-known mediated pattern in software engineering. What it does, you have a command tower that talks to all the planes and tells them what to do. So mediator has two functions. First, it talks to each of the actors, and second, it imposes policies on those actors. Who lands first, right? Who goes in an extra loop? But actors are responsible for their own state. They decide what to do. So if you take the policies out of the mediator, you get an event aggregator design pattern. This is also a well-known pattern. There is a link in the references to it. And what it does, it decouples publishers and subscribers from each other. And Mark, get that? Oh, I'm sorry, I was shining laser in that direction. I'm sorry. And Mark Yednek, on his presentation today, they implemented a message broker that gives them the same benefits. It decouples publishers and subscribers, and it does it through topics. And you can have multiple publishers published to the same topic. You can have a single publisher published to one topic. This is enforced by my framework. And you can have multiple subscribers subscribing. And this event aggregator doesn't have to be an actor. It can be a BioValue class, because it only handles the publish and subscribe requests the way I did. And the extra benefit is that there is no more constraints on object initialization order, because whether this guy wants to subscribe to topic, this topic doesn't exist, it will be created on first request. So that makes things much simpler. This is the UML diagram, which I didn't want to go into. I did a presentation on the CLA Summit 2015, covering this in detail. There's a reference there, go and look at it if you're interested. What I want to mention is that a message broker is not just, the reason I called it a message broker is more than an event aggregator. It also implements message translator, because its main purpose is to bind independently designed and probably in message incompatible systems. So a message translator option is what is expected. You may not want to use it. I don't have it implemented it now, but it needs to be able, you need to be able to add it. So that's my next step with message broker. Okay. And this is how the message broker works. So you have a subscriber, and the message broker has 4 methods in the interface. It's a BioValue class. Subscribe, unsubscribe, you say, you tell a topic name and give it your message transfer, where to send the messages back. And what it does, it maintains the topic list, and it counts the number of publishers, and has a message transfer. For some reason, I will talk about this now. And the publisher calls a register to publish and a register to publish with the same things, topic name and topic message transfer. But in return, it gets a transfer of an actor. A message can include that message broker spawns for each topic. And once it gets it and it wants to publish it, it creates a message and creates a message and calls send message to this guy. This guy has all the subscribers in the list, and it does the broadcasting of the messages. This is a way to avoid extra jitter in the publisher. It is done in a separate loop that is specific to a topic. One topic actor per topic. There is another option to do it if you don't care about the jitter. You can do publishing from this loop. So As a developer, for a specific topic, you can choose either thing. So that's pretty much how it works. And it looks really simple. This is the entire message broker interface here. It's like probably 7 or 8 classes. 4 of them are abstract classes. And this is the code. You don't need to read it. This is an example of a single publisher and 2 subscribers. And subscribers use different message transport. This uses LabVIEW, this uses events. And they can be served by the same publisher. So you initialize broker, same kind of thing like in the Zebra implementation. And it has an API, which is a by-value stateless class. You can branch it in LabVIEW and pass to different areas of your application. And in order to publish, a publisher says, okay, register me as a publisher, and this is the topic name, and it's done. And these 2 guys say, register me as a subscriber, and register me as a subscriber. And then they start running the loops, and they check messages for the strict message type that comes, and take the messages they want. This is a working thing, and to publish, you just create a message and use the message transfer to push it to the guys. So as simple as this, and at the end, you need to close the message broker. That's it. Very lightweight. It took me 2 or 3 weeks to put this together, but I was doing it in different ways for 5 or 6 years before. So it kind of came together in my head. That's why it didn't take so much. This 2 or 3 weeks actually tell more about how small the interface is, because the concept is not trivial. It's hard to get to a really simple decision in 2 weeks. Okay. Not important. There are 4 types of decoupling. There is actor decoupling. There is spatial decoupling. Publishers and subscribers do not know about each other. They're decoupled through the message broker. Temporal decoupling. The publisher doesn't need to be running for subscriber to subscribe. They're decoupled at time. Synchronization decoupling. Publisher and subscriber don't need to be available at the same time, because if the message transport is buffering messages, they would eventually get them. They may be doing some important job, and then they'll get all the messages if it's not a lossy message transport. And the last one, semantic decoupling, is the message translation feature. So that's the runtime decoupling. Pros and cons of message broker. The important message is, this is the good stuff, and there's no bad stuff that I see so far. So pay attention to the design pattern, do your due diligence. This is what I use now, and I intend to use it later. Right now, it runs only inside the address space, inside an exe. But by doing a message transport that goes across the boundary or across the targets with TCP/IP, without changing the message broker logic, I can communicate to remote message broker as a proxy. So that's an easy way for extending it. References, lots of references. You may want to look through them. Lots of Alan Smith stuff here. Yeah. And
Might have said a thing or 2 about actors.
yeah. And finally, I couldn't resist giving another quote by the author of The Little Prince. A designer knows he has achieved perfection, not when there is nothing more to add, but when there is nothing left to take out. I really like this. This is a big value for me. And the summary, the take-home message is, consider using solid principles if you want your code to adapt to changes and requirements at incremental cost. If you want to substantially increase code reuse levels, or you want to enable design of plugin architectures at no extra effort. Second one, actor designs based on command pattern are solid and friendly. Keep this in mind and do your due diligence. They are not good or bad, they may be good for you. They're bad for me. That's why I don't use them. That's what it means. And take a look at Message Broker because it is solid compliant, it supports hybrid messaging, which will make your life a lot easier. Okay, then you can take the survey if you want to. Maybe get another presentation next year. And questions, or I can tell you what I like in After Framework and what I dislike. That will take 2 minutes. You want to go through this?
I want to see it.
Or questions? No, let me do this and then the question. Okay. So first I did the slide in 2015. It was like first 4 items. I like Actor Framework because it's an elegant design. It is a scalable design. This wasn't true then. Now it comes as part of LabVIEW. This is a very important thing. It has a really vibrant user community, which is also a very important thing to people. And I provide customer support for Actor Framework questions. But the most important as a software architect for me is that Actor Framework really started a meaningful discussion in the LabVIEW community about Actor programming. Whether you use Actor Framework or not, this is extremely important. That's why we're here in this room, actually. Now, why don't use it? First of all, it's solid and friendly, and for me, this is a big thing. So I don't use any command pattern-based efforts now. IF actors are tightly coupled to their message transport, the enqueuer. I really don't see much value in this. I did the decoupling several years ago. Extremely happy with it. Again, the matter of unconditionally executing. There may be different opinions, as John said. Maybe it's true, maybe it's not. Decide for yourself. The next big thing, is Actor Framework bundles together the step of creating and configuring an actor and running it. You get the enqueuer only after you start an actor, right?
Correct.
Correct. And this is bad for dependency injection the way I use it. Because what I do, I configure all the connections in the assembler before the actors start running. Because you need to know application-specific details in order to configure connections. So that's a big thing to me.
So bad for dependency injection in your context.
Yes, yes. But I'm talking in my context. Right?
Okay.
Okay. Using publish subscribe in Actor Framework is too complicated. Adds a lot of boilerplate code or requires tool to help you with this code. Publish subscribe is absolutely essential to me because I use hybrid model. Okay, Actor tree, it's not a requirement, it's a recommendation, so I can drop this. This is a big thing for most people. You have class number explosion because of the message classes. You can use Allen's tricks to minimize them, but it's still a lot and it bogs down LabVIEW even on mid-size applications. It has a very steep learning curve. People need time to get their hands around this because this is just thinking a very different way. And as a consultant, for me, what is important, that the mainstream LabVIEW developers that my customers have, they have issues understanding and supporting Actor Framework-based projects. They need to go to Allen's classes, they need to wrap their head about it, and they start complaining this is too complex and you shouldn't charge you like 2x hours for what you're doing in Actor Framework, etc., etc. But nevertheless, I truly like Actor Framework, and I think it's a good development, and we should all do our due diligence and see the value that it brought to the LabVIEW community. Okay, questions?
I would just add one thing to that list that I've discovered with command pattern in general, which is what by Actor Framework, is that the design of your system is no longer on the block diagram.
Yes.
So it's very hard to follow what you did or what you're doing, because really you have to organize your project to uncover your design, or you have to do a lot of diagrams outside of LabVIEW to document what you do and how it works.
Yeah, because you have really many message classes that spread in space, and then you're not supposed to do blocking request reply as you can do with structured data flow. So these are two things. Yep, agree. Anybody else?
I had a question on one of your early slides.
Can you speak, bro?
I had a question on one of your early slides, the Liskov substitution principle violation with error codes. Can you
Yeah.
define a set of error codes that a method can return and have your children translate their errors to those?
They can, but the error should be defined in the abstract class.
So that's what I'm asking.
Yeah, you
Define a
can
set
do
of
message
errors.
translation, of course. Because what eventually would get to the caller is the translated message, no problem there. Anybody else? Well, thank you very much for coming. And people who don't have the solid ribbon and read or have the book can get their solid ribbons now.